Hi, everyone, and welcome back to another MathCounts hour at MetaPrep. So today we're going to work on the last 10 problems from the 2018 MathCounts State Sprint Round. And let's work through these problems. We're going to cover them really, really well. You ready?
Yes.
Skipping to the second to last page. Let's start with number 21. I'll give you a moment to work on this.
$32.
32. I'm not quite done yet. I think I'm definitely getting more than that. So go back and work on your answer for a little bit again.
$92.
It's gonna be a little less than that. So this is a challenging one to start off with here. A lot of the toughest problems at MathCounts are these kinds of geometric counting problems. And let's cover two different ways to do this. So right here, I've drawn out the picture. I've started to set things up. And we can draw this line and note the lattice points that are along this line, right? Because what we're using here, this line that we're graphing, it's a linear Diophantine equation. And every time x goes up by 1, the left-hand side goes up by 3. So we need y to decrease by 3 in order to counteract, or y to increase by 3 in order to counteract that. So we go from -24 to -21 to -18. And then we can count the lattice points sort of above each one of those red points that are along the diagonal. And so how many are above that first red point at 1, -21?
20.
20, that's right. How many are above the next point?
Oh, I see where I messed up. I accidentally counted the ones on the line too.
You were still off by a little bit if you did. So what's the series that we need to sum?
Um, 20 plus 17 plus 6 plus 14 plus 2.
Okay. And how many terms are in the sequence, the series?
7.
7. So what's our answer going to be?
$77.
77 is our answer.
Uh,
So this is kind of cool, but this is a fine solution. But I thought of a second solution. This is actually the one that I did before I finished drawing the picture. Was I looked at this and said, "Hey, triangles are kind of tough to count in, right? But what's easy to count in is a rectangle."
oh, and then you divide it by 2.
So you're close. What do we have to do to the number of lattice points inside the rectangle before we divide by 2?
Subtract the ones on the line.
Subtract the ones on the diagonal. How many will there be on the diagonal?
7.
7. So how many are in the grid in total?
22 times 6.
Oh, you're close. It's an 8 by 24
Oh,
rectangle.
23 times 27.
23.
Wait, 23 times 7.
23 times 7, good. So 23 times 7 minus 7 divided by 2. And that also gives us 77. And that's my preferred answer right there. I bet that more people do it this first way. But, if you can recognize some kind of nice fit or symmetry or something like that, very often you can use the bigger picture to help you solve the problem. Okay, let's take a look at the second one. Problem 22.
Wait. Oh, it's So it's 3 plus 1/8 plus 1/64.
Good.
So it's 3.11.
That's right. So what is our answer?
2.
Good work. Okay, let's take a look at problem 23 then.
Oh, I've seen this one before.
Have you?
Yeah. Wasn't there like the Monty Hall problem with 3 doors and like one of them holds the prize?
Well, have you seen this specific problem, or have you just seen the Monty Hall problem?
I've seen this specific problem
Have you?
too.
Okay. Well, let's try to work this again. I have not read it yet before, so I'll
I
do that now.
you should know. Hmm. Hmm. Is it like a 1/10 chance you would pick it on the first try?
Okay.
But then doesn't it change to 1/5 because there are only 5 boxes left afterwards?
So no. The opening of 5 boxes doesn't mean that you were luckier than you were before, or that Brian was luckier than he was before.
Oh. So the other boxes have 1 minus 1/10 divided by 4.
That's correct. And what does that equal to?
9 out of 40.
Good. That's the way to think through this problem. A couple of things about this. In order to help hone your intuition toward thinking in the right way, the fact that, Carl opening 5 of those boxes didn't really change whether or not you had chosen the one that was the correct one at the beginning. One thing to think is he's given new information, right?
Oh, it doesn't mean it necessarily changes.
That new information changes something, but it didn't change whether or not you had drawn the original box. He could pick 5 empty boxes to open one way or another. And so that additional probability is spread among the other boxes. On the other hand, we could say, what is the probability of A given B? That's equal to, do you know what that's equal to?
No.
Oops, I wrote it the wrong way. Probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. Let's talk about why that is. If this is the region of selection for some probability, and then we have a successful group here in blue, but then we're given some information, some condition that narrows the allowed samples, right? That condition is B. the blue, the success statement is A, right? So
Yeah.
the probability of A given B is no longer in the black zone. We only look inside the red zone.
Ooh.
And inside the red zone, there's the part of A that is inside the red zone. We want that shaded portion out of the total red zone. That shaded portion is A intersection B. And the red zone is B. Make sense?
Yeah.
So we want to know the probability that Brian's box is the correct box, given that 5 boxes were open. But 5 boxes were open regardless. That's still, in this case, just the probability that he had the original box. And the probability that 5 boxes were open is just 1. That happened, right? So it's a kind of a trick conditional right there, where you just wind up with the same probability that you would have had otherwise.
Oh.
One day we'll work a few additional examples, that are from kind of different angles, different ways to, to test these ideas, and we'll get better at this at some point in time. But for now, let's move on to problem number 24. Ivory writes down 3 two-digit numbers, each with units digit 7. The tens digit of the product of these 3 numbers is 5. What is the tens digit of the sum of the 3 numbers?
They're all wait, oh. The 3-digit numbers could be different, right?
3 two-digit numbers. They can be different.
Oh, so the 490 and the 343 are the ones that really matter, since those two have to become a 5 in the tens place. A plus B plus C has to equal 9, right?
Let's see. I was thinking the same thing, but I just looked over and it doesn't look like that's the correct answer.
Shouldn't it just be 9?
I want to make sure that I haven't misread this. Are we doing the same thing?
Yes. Hmm.
Oh. We did misread. I think we both misread. Look at the actual question.
Wait.
It's not asking for A plus B plus C.
Oh, it's 9, but you also have to add in the 7s in the ones digit.
Yes.
So it's actually 1.
1 is the correct answer. Oh, that's terrible. We both misread the problem the same way. What helps us keep from making that mistake on test day?
Rereading the question.
Rereading the question before putting down an answer, also circling a keyword, like sum. That's a good habit to be in. So yeah, I'm going to go ahead and write this out. All of this stuff, we know that the units digit of the product is going to be a 3. So this is all 53 modulo 100. And then if we subtract 343 from both sides, and of course, all that is 0 modulo 100. And we have, so 90 times A plus B plus C is 10 mod 100. And while we don't have division available to us, there is a theorem that allows us to take out a factor of 10 from the modulus if we take it out from the numbers on both sides of the congruence. So we wind up with A plus B plus C being the multiplicative inverse of 9, which happens to be 9 modulo 10. So, okay, A plus B plus C is 9, but what we want is A plus B plus C plus 2. Okay, let's take a look at problem number 25 now.
Casework?
Casework, what are the cases?
Oh. They're all less than,
Say again?
they're all less than a third.
That doesn't have to be true either.
Wait, oh, one could be like a ninth and then the other ones are really, really small. not
I think you mean
0.
0.9. One could be 0.9 and the other one's really
Yeah.
small. That's
Yeah.
true. It's true. What kind of probability is this if we can't like count stuff up to put it into cases?
I don't think I remember the name of it.
Here's a question. What if I said two numbers were randomly selected between 0 and 1? What is the probability that their sum is less than a half?
Don't we have like a unit square? Oh wait, you could just draw it, like put it on the graph.
That's right.
Oh, so
Right.
it's the one that connects 1, 0, and 0, 1.
Well, I made this one less than a half. And there, that red region is where x plus y is less than a half. And the square region, the bigger square region around it, is the total region of selection. So that probability is 1/8. So we want the size of the successful region over the size of the total region.
Is it just that tiny region?
Well, what is it for the 3 variable problem? What do I need to draw?
Wait. So that means if those are sum up less than a half, does z have to be less than a half?
Well, this was a separate problem. I just created a separate problem just to get us thinking about continuous variables. But now we go back to our problem. What is the probability that x plus y plus z is less than 1, given that they are all real numbers between 0 and 1? What should I draw?
A line? Should it be not
There's an x-axis. What else do we need?
a y-axis?
True. What else do we need?
Another axis?
Yeah, a z-axis.
Whoa. So many axes.
You haven't drawn many 3D coordinate axes before?
No.
Okay.
The only one I think I've done is like a triangle thingy. It's like this triangle thingy.
Well, this is something that you'll see more and more often. It's probably good to start getting used to it. And our total region of selection is going to be a cube. There's 1, 1, 1 over here in the corner. But what we want is x plus y plus z is less than 1. And by the way, x plus y plus c equals 1. That's the graph of a plane. And it happens to go through this point, and this point.
Isn't that like an ace?
So what we want is the region closer to 0, 0, 0, where the sum is less. So
It's an ace, right?
is it?
Wait.
What kind of shape is it that we're finding the volume of?
Trapezoid. No, wait, no. Pyramid.
Yeah, it's triangular pyramid. And the volume of triangular pyramid is 1/3 times the area of the base times the height. What's the area
It
of the
should be
base?
1/6. 1/2. and the height is 1, so it's 1/6.
That's right. So our answer is 1/6 out of 1, which is just 1/6. You like that one?
Yeah.
And this is the kind of it feels tricky at first. This is one you know, if we didn't kind of have time limits on a test like this is a good one for you to be chewing on right now, because I bet that just given a lot of time, you'd have, you know, time to begin to grasp onto what this is without any help. I've seen the way that you go after problems like that before, but now this is something that you can begin to get used to. You know, notice that I wrote size of the successful region over size of the total region. You've worked these problems with one variable or two variables before. Well, you know, really 3 variables is mostly just a matter of you learning to reach into 3D geometry, and in particular this time with coordinates. And you know, it's not so crazy hard. It's probably, this is an easier problem for somebody who knows the equation of a plane, right? AX plus BY plus CZ equals 1 or something like that. If you know the equation of a plane, and you know, and you understand what that is, then you know it's a matter of just finding, you know, convenient points on the plane on the boundary of the cube to help you draw out what the region is. So that was our idea. All right, let's continue to problem 26. Keep reaching for that answer key, but I don't need it there. Kevin writes a sequence of numbers starting with 1 and repeatedly adding 1 until a multiple of 2 is reached. He then repeatedly adds 2 to this value until a multiple of 3 is reached, then adds 3 until he gets a multiple of 4, and so on. The first 4 terms are 1, 2, 4, 6. What will be the last term Kevin writes down before he adds 2,000 for the first time?
Sounds like a weird thing somebody would do.
Sounds like a weird thing somebody would do.
Yeah. Wait, doesn't it just go up by 2 each time? You add 2 of the terms? Like you add 2 2s to get to 6, and then 2 3s to get to 12? And then 2 4s to get to 20?
Sure looks that way. Can you prove it?
Isn't it like always 2 less? Because 6 is 2 times 3, and 12 is 3 times 4, and 4 is 2 more than 2.
Okay, it certainly looks like that. Let's assume that's correct for the moment. What would the answer be?
Uh, 3999.
Don't compute, just tell me what you do to get that answer.
Oh, there's 199 of them before you add 2,000, and then you multiply it by 2 because you added 2 times, and then you add in the 1 at the start.
199 of them?
Wait, 1999.
1,999?
Yes.
So what the answer is going to be what times what?
1,999 times 2 plus 1.
Times 2,000 plus 1?
Times 2?
Well, let's be careful. What if we reformulate the problem for a simpler answer? What if instead of, what will the last term Kevin writes down be before he adds 2,000 for the first time? What if we said, what's the last term he writes before he adds 5 for the first time?
Oh, the last term I said. 2 plus 2 times 2 plus 2 times 2 plus 3 plus 4 plus 2.
We have the first 10 terms of the sequence in blue.
Oh, it should be 16.
Not 16.
$20? $20, I think.
It's 20.
So it should be 1,999 times 2,000.
Seems like that's going to be the answer. Let's make sure that we know for sure. When we get to n squared, when we've just added n, so then we add n plus 1. Sorry, that was after the first time we add n. So then we add n again, which gives us n times n plus 1. And then we add n plus 1. To get to n squared plus 2n plus 1, which is n plus 1 squared. So we have, every other term is a perfect square. And the ones in between are these n times n plus 1 terms.
Oh.
And we can see that we add, right before, between adding 4s and 5s, we have the term 4 times 5. So yeah, 1999 times 2,000, and that gives us 3,998,000. These are pretty tough, aren't they?
Yeah.
Okay, let's keep moving forward. Oliver rolls 3 fair standard 6-sided dice. What is the probability that there is at least one pair of dice whose top faces sum to 6?
Find a number of dice that sum up to 6. Like, do we just count one pair and the other pair doesn't really matter?
Well, we just need for one pair to work out of the 3 dice, right? We have 3 different possible pairs to choose from.
So we just count a pair 2 pairs that work, and then the third one doesn't matter.
How many different ways, how many outcomes are possible?
6 cubed.
Okay. How can we proceed? Do we just write out the 6 cubed possibilities?
No, this one of the cubes doesn't really matter. So it's just 6 ways to get that one.
What do you mean one of the cubes doesn't matter?
Because you only need at least one pair whose top faces sum up to 6.
Yeah, but that one cube participates in 2 of those pairs.
Eh. Hmm. Hmm.
Want me to give us a start?
Sure.
So my thought was this is probably going to be a casework problem. I was kind of, looking to see if I could find something that lent itself to an easy solution like a symmetry or something like that, but I don't yet notice anything. Maybe we'll find something like that, but I don't see it yet. So I thought of 2 ways to break down the casework, and we'll go after one of them. The first one that I thought of was, cases in terms of the first die. And the second method I thought of was in terms of the ways to sum 2 dice to get 6. And I'm going to go with method number 2. In this method right here, we can say, hey, we're only going to get a sum of 6 if we have a 1 and a 5. So that's our first case. A 2 and a 6. Or, sorry, 2 and a 4. Or a 3 and a 3. So in how many different ways, the nice thing about these 3 cases is, there's nothing overlapping, right? There's no way to get a 2 and a 4 and a 3 and a 3, for instance. That would require 4 dice. So with 3 dice, we're still in this nice zone with no overlap. We don't have to worry about principle of inclusion, exclusion, or anything like that. So let's count up the number of ways we can have a 1 and a 5. Or at least 1, 1, and at least 1, 5.
Mm-hmm.
What could the other die be? What could the other die be?
Hmm. Wait, so for the first case, there are 6 more ways for the other dice roll?
Okay, so we can have 1, 1, 5, 2, 1, 5, 3, 1, 5, 4, 1, 5, 5, 1, 5, or 6, 1, 5. Is that what you're telling me?
Yes.
Okay, that's true.
And
What
then
else could say again?
and the same for the other 2?
Well, let's finish this case first. In how many ways can we get these outcomes from 3 dice?
Oh, the first one has 3, and the other ones have 6.
First one has 3. This
6.
one has 3 factorial.
3 factorial, 3 factorial, 3.
Okay. And if we add all those up, what do we get?
30.
What's nice about case 2?
The same thing, 30.
Yeah. Case 2 is symmetric to case 1. Getting a 2 and a 4 is the same, the likelihood is the same as the likelihood of getting a 1 and a 5. It's just likelihood that 2 particular dice come up amongst 3 rolls. Okay. The last case is different though. We need 2 3s. So we list out the possibilities as before. A 1, a 3, a 3, a 2, a 3, a 3, 3, 3, 3.
4, 3.
And now among these subcases, what do we do?
Reorder them.
How many permutations?
3, 3, 1, 3, 3, 3.
In total?
16.
Okay. So what's our answer going to be?
76 divided by 6 cubed. 32 divided by 3 cubed times 2 squared. 19 divided by 54.
And that is correct. So what was the hardest part of this?
Finding a way to do it.
Finding a way to organize the casework?
Yeah.
But ultimately, notice that our organization wasn't that bad. I think this problem, it messes with you a little bit at first, right? Why does it mess with you a little bit at first? Because I've seen you organize much more challenging, casework than this before, right? There's something a little bit weird about this problem though, and it's worth stopping to think about like that. Like, why does this problem kind of throw you at first as a reader? You want to just set one die aside. Like, we don't even need this one.
Oh, because you have to order it.
Yeah, we do need to consider the interactions between all 3 dice when choosing the pairs. So we do have to kind of see them all together at once, in a sense. It's good to go through one of those and see the way that it confuses us momentarily. Okay, let's take a look at number 28. What is the percent probability that a random point chosen on arc CD forms an acute triangle with points A and B? Interesting.
All but the bottom part of CD. Basically, you have to find a point where on CD that it forms the right triangle.
Okay, yeah, the border between acute and obtuse is where we get right triangles.
Yeah.
how do we get, if we have a triangle with vertices at A and B, where would we choose a third point that would make a right angle?
We have to choose it where the angle A and angle B have to be sum up to 90. But how do you pick that?
That's true.
But how do you pick that angle then?
Or is that the way that we want to think about this? When dealing with circles, how do you get right angles in circles?
Don't know.
What if I said you have an inscribed angle in a circle? How do you measure an inscribed angle?
With the arc,
What do you do with that arc?
you divide it by 2.
So how big does your arc need to be in order to have a right angle?
It has to be the half of the whole circle.
That's right. So what we're talking about is a diameter. If you have a diameter and you pick any other point on the circle,
it will form a right triangle.
Forms a right angle, and therefore we have a right triangle. So what we need is some point on this semicircle, and we need to figure out where that semicircle hits that quarter circle.
Ew.
And we want the proportion out here. We pick that point outside, our angle is going to be smaller. If we shorten it and pick it inside, it's going to get larger. It'll be obtuse. So we want that top part from C to, we'll call that point P right here. From C to P, we want C to P divided by arc C to D.
Don't know.
Well, maybe worst case scenario is we figure out the equations of these circles. One of them is centered around negative a half, I think. Is that right? No, that's not right. Pardon. And what is the radius?
Radius is 1.
Okay. What's the radius of the big semicircle? Or what's the equation of the big semicircle?
Y equals x plus 0 times y plus 0.
X squared plus y squared equals
0.
Yeah, and I picked 0, 0 at D. I don't know if I said that out loud, but you seem to follow along with that. X squared plus y squared equals, sorry, tell me again.
1 or is it 0?
You tell me.
0?
Well, what do we know about the square of any real number?
Oh, it's 1 because it can't be negative.
Yeah. We always have x minus center coordinate squared plus y minus center coordinate squared equals radius squared. Okay. Now what?
Solve for xy where it hits CD. Wait, find the equation of the circle that includes CDP.
Oh, that was the first one.
Wait. Oh, find the big semicircle, the equation of the big semicircle, and find out where they intersect.
Yeah, we might go down this path. I feel like this is probably easier. I'm going to redraw. We should be able to do this more geometrically, I think. It's 2-unit circles. One goes through the center of the other, so each goes through the center of the other.
Do you solve using those two equations?
Well, if each goes through the center of the other, then we have radius, radius, radius. Do you see that?
Oh.
Yeah, that's the key. Oh, I should have seen that sooner. Radius, radius, radius. So those are 60-degree angles over there.
Oh.
So what does that mean? That's a 60-degree angle. So that's a 30-degree angle.
So you can find a point? Oh, so you could then find the arcs. So it's 2 to 1, I think.
Well, I think what we want is not the ratio,
Oh.
but the probability that a point on arc CD is also on CP.
Oh.
So I think we just want 1/3 and turn that into a percentage. I'm gonna
3.333.
Yeah, the answer is 33.3. So we've done ourselves right at the end there. That's good. This is a good. This is the type of thing that I would always loved to save time during tests. If I could work the first 15, 20 problems relatively quickly, then I had the opportunity to not see the easiest solution first. And at first, when I was drawing this, I think I fooled myself into thinking the circles weren't the same size, right? Because we're only drawing part of the arcs, and maybe a picture isn't perfect at first. Maybe that would have been worth thinking about before diving into the problem, right? Oh, these are circles of the same size, therefore, that go through each other's centers. And I've dealt with those many times before. You've probably seen some problems with circles going through each other's centers.
Yeah.
Maybe just a little bit. At some point it'll become old hat for you, but if they're the same size, we get those equilateral triangles on, well, 2 equilateral triangles in between that nice rhombus. Okay, but it's good to have time to go down one path and go, I bet there's an easier path. Okay, problem 29.
It's already 6.
You're right, it is. Do you want to stop here, or do you want to finish the last 2?
I don't really mind.
Okay, then we'll keep going. Let's finish the last 2. Maybe we'll try to do these quickly. Congruent non-overlapping circles A, B, C, and D are plane such they're mutually tangent, and circle D is tangent to circle C. Triangle EFG circumscribes the 4. If the radius of each is 1, then the length of FG. Okay. Here's what I'm going to do. I'm going to, I want a bigger version of the diagram. So when I see a problem like this, I'm thinking about equal tangents. And I'm thinking about breaking FG up into parts.
Could it possibly be a 30, 60, 90 triangle?
Oh, goodness. I don't know if we have enough to make that kind of assumption.
Kind of seems like it.
But what I do know is that FG is equal to X plus Y plus 4. And, you know, we have equal tangents from a point, right?
Mm-hmm.
So one of our sides is X plus C plus 2. One of them is Y plus C. Oh, this one here is tougher. Huh.
It would look like a right triangle since it's BD is 4 and AB is 2. So if BAD is 90, then AD is square 2 root 3.
Good. And it now here's the thing, you know, in the last problem we saw those equal radii give away an angle. We do have a 60-degree angle. And then we go over to triangle ACD. And what do we see?
Angle CAD is 30.
Actually, I don't even think we need to know that. I think we just need to know that AD is parallel to EG and that BA is perpendicular to EG. So this is a right angle right here. We do have a right triangle, and it is a 30, 60, 90 right triangle. So that length up there is 2 root 3. So good that you were looking for special triangles. Now, how does this help us?
Z is 1, right?
How do you know?
Since it's like it creates a small square there.
You are correct. Oops. Good. What about X?
Oh, X is square root 3.
Good. Now, Y is the toughest one.
Square root 5?
No. Is that a 15-degree angle right there?
Wait, Y is 3? Is Y 3 or not?
No. Have you seen the ratios of sides? Let me think about this for a moment. You and I have not done trigonometry yet, have we?
Not much.
Okay.
Isn't that tangent of 15 is equal to 1 over Y?
That's right. Okay, good. That's what I was about to do.
So cotangent of 15 equals y.
We want the cotangent of 15. And since we're short on time and I was just told that it's dinner time in my household, I'm going to go ahead and tell you that the tangent of 15 degrees is 2 minus the square root of 3. And so the cotangent is 2 plus the square root of 3. The total length of FG is going to be 6 plus 2 root 3. And so the final answer is going to be 11. And unfortunately, we do not have time for the third problem, but yeah, we'll do that another time. We'll do number 30 sometime soon, okay?
Okay.
Well,
Thank
thanks
you.
for joining me, and I'll see you on Sunday.
Bye.
Bye.